Hey everyone, this is Dr. Gilbert. In this video I'm going to go over the answers to the questions in the first section of the 2018 first midterm test. So prior to doing anything, I would first recommend that you read the instructions very carefully. On this test, the first section consisted of multiple choice questions, true or false questions, and a few fill-in-the-blank questions. For the multiple choice questions, we're told to circle the answer label which best answers the question, and that in some cases more than one answer may apply. So let's take a look at this first question. It says, which of the following ideal bond graph elements can remove energy from a system? The inertance and capacitance are storage elements, but the other two, the resistance and the effort source, are both capable of removing energy. In the next question, we're asked to write the formulas for the kinetic energy as a function of momentum stored in a translational mass, and the potential energy stored in a linear electrical capacitor as a function of the charge. So these formulas are standard. The kinetic energy is p squared divided by 2m, and the potential energy is q squared divided by 2c. In the next question, we're asked whether the power into a resistance is always greater than or equal to 0. In other words, is the product of the effort and flow variables always greater than 0? And this is true. The ideal DC motor is best represented by a gyrator out of these choices. We label the signals in the block diagram according to the causal stroke between the two subsystems A and B. We're now asked to write the SI unit and name for the power variable in each of the energy domains that's listed in the table. For mechanical translation, we have force in newtons, and we have velocity in units of meters per second. For mechanical fixed axis rotation, we have an effort variable of torque with units of newton meters, and a flow variable of angular velocity with units of radians per second. In the electrical domain, our effort variable is voltage, which has SI units of volts, and the flow variable is current, which has SI units of amperes. In the hydraulic domain, our effort variable is pressure in units of pascals, and our flow variable is flow rate, or sometimes volumetric flow rate, in units of cubic meters per second. This next question asks us to determine the value of the variable E2 given the bond graph that's shown. So we begin from the law for a one junction, which states that if we sum the effort variables on all the bonds with power directed into the one junction, this must equal the sum of all the effort variables with power directed out of the one junction, on bonds which have power directed out of the one junction. So this gives us E1 and E3 on one side of the equation and E2 and E4 on the other. We can simply rearrange this for E2 to get the answer to the question. In this next question, we're shown several engineering subsystems and asked whether they have the fundamental behavior of a transformer or a gyrator. So the DC motor is a gyrator, the lever is a transformer, the fluid piston cylinder is also a transformer, the wheel is another transformer, the mechanical gyroscope is a gyrator, positive displacement type pumps are transformers, and the electrodynamic loudspeaker is a gyrator just like an electric motor is. Now this last problem is a bit more complex than the first 8 problems in this concept section of the exam. The prompt is that we have a rubber air-filled ball. It weighs 0.1 kilograms, and it's going to fall from a height of 10 meters. So it starts out with no velocity, and after we let it go, it falls the 10 meters, and when it hits the ground, it will reach a point at the bottom of its impact where again it has no velocity. And you see that the ball has been compressed, and we label the amount of compression at the surface of the ball with a delta. So it's our job to try to determine the stiffness that relates the ground reaction force with this deflection variable delta. The way we're going to do this is by assuming that if there is no air resistance and there are very few losses in the materials when the ball impacts the ground, then the amount of energy in this system before has to equal the amount of energy in the system after at the bottom of the impact. The energy before is due to the potential energy of the ball above the ground, which we'll say is mgh, and the energy after consists of both the potential energy stored in the compression of the material and the compression of the air on the inside of the ball, and we also have a negative potential energy of mg delta. So all we have to do is rearrange this equation for k. We get that it's equal to 2 over delta squared times mg quantity h plus delta. So the ball falls a total distance of h plus delta, which you can see from the diagrams. We can plug in the values that we were given for these variables. And the arithmetic is not exactly fun, but it's not too bad. We at least get to cancel out 0.1 in the numerator and denominator. Go ahead and do the division of 2 divided by 0.1, which is 2 times 10 is 20, times 10.1 times 9.81. We finally work our way to an answer of 1,980 newtons per meter stiffness. Now the question only asked for a rough estimate of the ball's stiffness. So in actuality, if anybody got an answer relatively close to this, they were given credit.